Okay, so we're now recording. Okay, let me go ahead and share my screen, and I'm going to show you guys what is in Schoology. Okay, so today is going to be a very simple day in that we are continuing our conversation into standing waves. Remember, we talked about standing waves on last class period. I introduced that to you guys. I showed you guys several examples of standing waves utilizing the video from Bozeman Science. That lecture is still on my YouTube page. So if you go to my YouTube page right here where it says physics class March 29th and March 31st, you guys can still look over that if you want to go over those concepts from last time in more detail, because some of those concepts will be on this assignment for today, because this assignment for today is called Standing Waves Part 2. Okay, so that is still on my YouTube page for those of you guys who want to look over that. All right. So um so remember last time I showed you guys what a standing wave looks like. Okay. And this is what a standing wave looks like right here. It's exactly what it sounds like. A standing wave is a wave that just stands there. Obviously, it's not. If you look at this wave, according to its appearance, the pulse of energy does not appear to be traveling from here to here. In fact, the wave just appears to be just standing there, just bobbing up and down, bobbing up and down. So as it sits there and bobs up and down, we call this a standing wave. Okay. Now, remember what I told you guys last time. All standing waves have nodes and antinodes. Um, so the nodes, and again, we talked about all this last time, so I'm not going to, write down the definition. I'm just going to show it to you, point things out to you guys. So the nodes represents the region of no displacement. So if you look closely at these regions right here, the wave is not moving at those points. So those points in red represent the nodes. That's the regions of no displacement, because the string is not moving at those points. Node, no displacement. Okay. These regions in blue right here, so that region in blue, that region in blue, that region in blue, that region in blue, those are our antinodes. Remember, antinodes are the regions of maximum displacement. That's right. For example, look at this. Look at this wave here. So either the wave is at its highest point here, or its lowest point here. So the wave just keeps going back and forth from its highest point to its lowest point. Okay, so those are our regions of maximum displacement. So the antinode is the opposite of the node. Okay, so the node is where we have no displacement, and the antinode is where we have maximum displacement. Okay, so that's just something to keep in mind for your assignment on today. So we also talked about harmonics. If you guys remember what I said, that a standing wave can vibrate at different harmonics. Okay, so for a standing wave that's vibrating at the first harmonic, that will look something like this. Remember, guys, if a standing wave is vibrating at the first harmonic, which is also called its fundamental frequency, its natural frequency, it looks something like this. So if it's vibrating at the first harmonic, it always has one antinode. Okay. If you have a standing wave that is vibrating at the second harmonic, that standing wave would have two antinodes. Okay. If it's vibrating at the third harmonic, it would have three antinodes. So you guys can see the pattern here. So if you had a standing wave let's just say you can imagine you have a standing wave that's vibrating at the 1000th harmonic. And that means that standing wave would have 1000 antinodes. Okay, so the number of antinodes always matches the harmonic number. Okay, so just something to keep in mind. And remember what I said last time, the number of nodes that you have will always be one more in addition to your number of antinodes. So if you have one antinode, that means your standing wave has to have two nodes. But what if we move on to the second harmonic? For the second harmonic, if you have two antinodes, then that means you're going to have three nodes on that standing wave. if you move on to the third harmonic, that means you want to have 3 antinodes, which of course means you should have 4 nodes on that standing wave. So obviously a standing wave that's vibrating at the fourth harmonic has 4 antinodes and 5 nodes. So everybody get that? Okay. Now, and of course, here's a basic visual of the patterns. So here's 1 antinode, first harmonic, 2 antinodes, second harmonic, all the way down to 6 antinodes, the sixth harmonic. That will look something like this. Okay, so hopefully that makes sense. Those of you guys that are just now coming in, please fill out the attendance form. Okay, now the last thing that I want to talk about today, and this is the only new thing that I'm going to talk about today, is the mathematics of standing waves. The mathematics of standing waves. So, guys, it turns out that each harmonic is represented by half a wavelength. Okay. Let me give you an example of what I mean by that. So, imagine a standing wave that's vibrating at the first harmonic. Okay. So if a standing wave is vibrating at the first harmonic, that standing wave is always represented by half the wavelength, right? Because think about it, if you think about a standing wave vibrating at the first harmonic, it's either up or down, up or down, up or down. Okay. But what about a standing wave that's vibrating at the second harmonic? If you notice, that's represented by 2 halves of a wavelength. Because think about it, guys. Think about it. Here's a half wavelength here, and here's a half a wavelength here, right? So that's the second harmonic. Okay. But what about a standing wave that's vibrating at the third harmonic? That's represented by 3 halves of a wavelength. So, right, because here's a half a wavelength here, here's a half a wavelength here, and then here's a half a wavelength here. Right. So basically, I'm drawing how the wave will look like at a single instance in time. Like if you have to take a snapshot of that wave, you will see 3 halves, 1, 2, 3. So whenever you are coming up with an equation that relates the length of the string to the actual wavelength itself, you're going to use these equations here for specific harmonic numbers. So these equations here off to the side are what you're going to be using for specific harmonic numbers. And of course, these are the equations you're going to be using in your assignment, okay, which is what I'm about to get started on now. Okay, so for the first harmonic, the length of a string is equal to 1/2 the wavelength. For the second harmonic, the length of a string is equal to 2/2 the wavelength. For the third harmonic, the length of the string is equal to 3/2 the wavelength. For the fourth harmonic, the length of the string is equal to 4/2 the wavelength, and so on. So these are the equations you're going to need to use for your assignment. Okay. Now, with that said, the last thing that I'm gonna do today, guys, I want to open up this assignment, and I want to go over some of the questions with you all, and then the rest you're going to do on your own. Okay, so the assignment's already open, so if you guys want to click on that and follow along with me. Okay. Some of these questions are easy. Like for example, right here, so it says how many antinodes does the fourth harmonic have? That should be easy, right? Because the harmonic number should match the number of antinodes. Okay. What I want to do right now, I want to look at a few of these questions that involve these equations here. I want to do some of those with you guys. Let me see, which one do I want to do first? Let me see. Okay, guys, look at this question right here. Let's do this one right here. It says a string that is 6 meters long is vibrating at its fundamental frequency. What exactly is its wavelength? Okay, so guys, remember, if it's vibrating at its fundamental frequency, that means it's vibrating at its first harmonic. So that means we need to use this equation here to find the wavelength. Okay, for the first harmonic, the length of the strain is equal to 1/2 the wavelength. So I'm gonna write this equation down for you guys. So the length of the string is equal to 1/2 the wavelength. Okay. So again, since we wrote this equation down, let's just plug everything in to solve for the wavelength. So as it says, our string is 6 meters long. So I need to plug this in for L because that's the length of my string. If my string is 6 meters long, and I want to solve this equation for wavelength, remember the symbol lambda right here, that means wavelength. How do I do that? How do I get lambda by itself? Okay. Well, guys, in order to get lambda by itself, remember I have to multiply by the reciprocal of 1/2. What is the reciprocal of 1/2? It's 2. So if I multiply this, if I multiply this side of the equation by 2, then that goes away, and whatever I do to one side of the equation, I have to do to the other. So 2 times 6 is equal to lambda. Okay, so what is 2 times 6? 2 times 6 is obviously 12. So my answer there is 12 meters. Okay. Guys, I'm gonna do one more question like this so that you guys will get the point whenever you guys understand, whenever you guys get to these questions on the assignment. Okay. So I'm gonna clear my drawings. All right, I'm gonna do one more question that's similar to this. Let me see. I think I saw it back here. Okay, guys, look at this question right here. It says, if a string vibrating at the fourth harmonic is 32 meters long, what is the wavelength of the standing wave produced by the string? Okay, so we're going to need to go back to our equations on this page here. So if it says if a string vibrating at the fourth harmonic is 32 meters long, okay, so guys, look at your equations here. Go to the fourth harmonic. Okay, what is the equation that relates the length of the string to the wavelength? Okay, well look, it's written here. The length of the string is equal to 4/2 the wavelength for the fourth harmonic. So guess what? I'm going to take this equation and I'm going to write this down here. So for the fourth harmonic, the length of the string is equal to 4/2 the wavelength. Okay. But guys, what is 4 divided by 2? You guys should know 4 divided by 2 is just equal to 2. So I'm just going to reduce this equation to 2 wavelengths. Okay. Now notice what it says. My string is 32 meters long. So I want to take this. I want to take 32 meters and I want to plug it in here for the length of my string. So I'm going to plug in 32 there. Okay. And I want to solve this equation for lambda. How do I solve this equation for lambda? Well, I have to get lambda by itself. In order to get lambda by itself, I have to divide this side of the equation by 2. That goes away. Whatever to one side, I have to do to the other. Okay. So what is 32 divided by 2? Okay, because 32 divided by 2 is going to equal lambda. In other words, it's going to equal our wavelength. Okay, so 32 divided by 2 is 16 meters. Okay. All right, guys. You guys are going to do a very you guys are going to do a similar thing whenever you guys, like, for example, get to this equation right here, and we'll get to this question right here where it says if a string is vibrating at 6 harmonic that is 12 meters long, what is the wavelength of the standing wave produced on the string? You would just go to the 6th harmonic, look for the equation, plug everything in, and solve for wavelength. Okay. All right. I think I'm gonna do one more with you guys. Look at this question right here, number 12. It says, if the frequency of a 4th harmonic is 40 hertz and has a wavelength of 2 meters, what is the speed of the wave? I want to do this with you guys because it's been a long time since we talked about wave speed. It's been, several days. So I want to remind you guys of the equation for the speed of a wave. The speed of a wave, I want to remind you guys, is equal to wavelength times frequency. Okay, so if our so in the problem, it tells us that our wavelength is 2 meters. Okay, and it tells us that our frequency is 40 hertz. Okay, so if you take 2 and multiply that by 40, what do you get? You get that 80 meters per second. Okay, the rest I want you guys to do on your own. Guys, whenever you guys are doing the rest on your own, remember when we did these examples in class last time. For example, if it gives you a standing wave and it tells you that the fundamental frequency of the first harmonic is 6 hertz, you can easily find the frequency of the remainder of the harmonic. So because all you do is just do the harmonic number times the original frequency. So for example, H2 would be 2 times 6, which gives you 12. H3 would be 3 times 6, which gives you 18, and so on. Okay, so keep that in mind. And remember, we talked about this last time. So for example, imagine that you have here the first harmonic, the second harmonic, the third harmonic, the fourth harmonic, and the fifth harmonic. Now, what if they ask you to go backwards? What if they give you the frequency, let's say here at the second harmonic, and they ask you to find the fundamental frequency, or in other words, the frequency of the first harmonic? So in this case, you would just go backwards. You would divide. In this case, I would do 20 divided by 2, which gives me 10 hertz. Okay. So for the third harmonic, my frequency is 3 times 10, which is 30 hertz. Here it's 40 hertz, and here it's 50 hertz. Okay. So we talked about that last time, so I just wanted to remind you guys of that. Okay, any questions before I let you guys go? Any questions? All right, guys, I'm going to put the attendance form in the chat box for those of you guys who have not filled it out yet. If there are no more questions at the moment, you guys are free to go. The Zoom call will be open up till 9 o'clock. So if you guys have any questions, feel free to, sign back in and let me know. Have a good day, everyone.